So let me start today's class.
Good morning, sir.
Morning.
Morning, sir. Morning.
Good morning, sir.
Morning. Now from today we are going to start the working stress method. Okay. So first of all, let me show you the working stress method is given in your IS code, that is in Annex B, page number 80. Okay. And there is some assumption. You can see first assumption is at any cross section, plane section before bending remain plane after bending. And now you know that what is the meaning of this section of this assumption, that is plane section before bending remain plane after bending, and after that all tensile stresses are taken up by reinforcement and none by concrete except otherwise specially permitted. Now what is happening when you going to design a beam? Then suppose this is a rectangular beam, and say this is the neutral axis. So this is the reinforcement. Okay. Now on the compression zone, the concrete can take the compression. Okay, that's why there is no problem. But in tension zone, concrete actually can resist 1/4 of the compressive zone, that is that resist the tension zone. Concrete can resist the tension strength. Tensile strength of the concrete is actually 1/4 of the compressive strength, approximately. Now you can understand that concrete cannot resist the tensile force. So what we have to do, we are applying the reinforcement to resist the tensile force, and to place the reinforcement at this particular position we need.
Sir.
Yes.
স্যার বলছি একজন হতে পারছে না, এন্ট্রি হতে পারছে না গুগল মিটে, একটু অ্যাকসেপ্ট করুন।
গুগল মিটে এন্ট্রি হতে পারছে না কে?
নাই বলেছেন।
When we place the reinforcement at the tension zone, and you have to place the reinforcement at the maximum where the maximum tensile stress is producing. Okay, so this is the bending stress diagram, and all those stress will be taken by concrete, and tension is at the bottommost fiber is the maximum tension is there. That's why we are applying reinforcement at the bottommost fiber. Okay, after that there is a cover. This is called cover of reinforcement. This is we place this cover due to the keeping in mind the environmental condition. Okay. Now concrete cannot take any tension. That's why we have to neglect the portion of concrete in tension zone. Okay. Now what is our actual what is our theoretical cross section? So this is the theoretical cross section. Suppose this is the neutral axis, neutral axis, and there is a virtual rectangular portion below the neutral axis, and we have only reinforcement. Okay, we have only reinforcement below the neutral axis, no concrete. Okay, so this is the second assumption of working stress method in provided you in IS 456. Okay, so all tensile stress are taken up by reinforcement and none by concrete, except and otherwise specially permitted. Okay, now the next assumption is stress strain relationship of steel and concrete under working load is straight line. What is the meaning of this assumption? Stress strain relationship of steel and concrete under working load is straight line. That means you know that the stress strain relationship of concrete is nothing but parabolic. Okay, so suppose this is the stress strain curve of concrete. Now if you see this position, you can find there is a straight line. Okay, now IS code is assuming this amount of linear or straight line portion for the concrete. That means in working stress method our stress strain curve of concrete should be this. Okay, and for mild steel or for steel, this is the stress strain curve of steel, and we are considering this amount. Okay, now again for steel, stress strain curve of the steel is this. So stress strain relationship is linear, and you can see the stress strain relationship of steel and concrete is straight line. Okay, now what is modular ratio? That is given in S456. Okay, now let us try to understand what is modular ratio. First of all, you assume a concrete, a steel. Suppose this is the cross section of the particular beam, and this is the reinforcement, and surrounding the reinforcement we have some concrete. Okay, so this is the concrete surrounding the reinforcement, and think about this particular position. That means suppose we have one concrete here and we have steel. We just assume that the very infinitesimal portion of this position. Okay, now we are applying a load, tensile force P. Okay, now after application of load, suppose you know that the stress strain curve of concrete and stress strain curve of steel is totally different. Both are linear but totally different because the material is also different. One is brittle material and that is ductile material. So we can say that after the application of load, this will be the elongation of the concrete, and suppose 1 minute. So this will be the elongation of concrete, and suppose this will be the elongation of steel. Now you can see that this is the elongation of concrete. Suppose delta C, and this is the elongation of steel. Suppose delta S. Okay, Now what is the formula of strain? Formula of strain is epsilon equals delta by L. Okay, so this is original length L. Okay, now epsilon C equals delta C by L, and epsilon S equals delta S by L. Okay, now the value of L is same for both case because the length is same before the application of load. Okay, length is same, but delta C is difference. Okay, so we can say that epsilon C is not equals to epsilon S. Epsilon C is not equals to epsilon S. But IS code is saying that you have to assume that epsilon C is equal to epsilon S. Okay, epsilon C is equal to epsilon S. You have to assume this assumption, you have to consider. Okay, this is called compatibility of strain. This is called compatibility of strain. That means for a particular application, for a particular load, for different type of material, okay, the strain is same. Okay, epsilon C and epsilon S both are same. This is called compatibility of strain. Now, why we are considering this this phenomena, compatibility of strain? We have to do something else. Now, suppose you know that stress by strain is equal to Young's modulus. Suppose this is sigma C, stress of concrete by epsilon C, strain of concrete. Okay, and we can say that this is equals to Young's modulus E of concrete. Okay, so stress by strain is equal to constant. Stress of concrete by strain of concrete is equal to Young's modulus. And again, we can say that stress of steel by epsilon of steel, that means strain of steel, equals to Young's modulus of steel. Okay, now our assumption is the compatibility of strain. That means epsilon C equals to epsilon S. Okay, we assume this phenomena, so that's why we can say that epsilon C equals sigma C by EC, and epsilon S equals sigma S by ES. Okay, now epsilon C is equal to epsilon S. Okay, so we can say that epsilon C by EC equals to epsilon S by ES. Okay, now epsilon S equals to, we can say that epsilon C multiply by ES by EC. Okay, and you can assume ES by EC as a one constant, because ES is a constant, that is value of ES is 2 multiplied by 10 to the power 5, okay, Newton per millimeter square, and EC is also constant, okay, and it is the another constant. Now you can say epsilon c multiplied by m, okay, that means m equals to ES by EC, m equals to ES by EC. So this m is called modular ratio, okay. Modular ratio, okay, this m is called modular ratio, and IS code is providing that this value of the modular ratio ES by EC actually as 280 by 3 sigma CBC, okay. IS code says that you don't need to consider this modular ratio as ES by EC, you just consider the value of modular ratio as provided by the IS code, that is 280 by 3 sigma CBC. And what is 3 sigma CBC? What is sigma CBC? Sigma CBC is permissible compressive stress due to bending in concrete, okay, in Newton per millimeter square as specified in table 21. In the first class I have shown you the table 21, that is provide us the value of sigma CBC for various grade of concrete, okay, and table 22 is providing us various value of sigma ST for various type of steel, okay. Now this is 280 by sigma CBC you need to consider. Now just assume that example, one is concrete and another is steel. This is concrete and this is steel, okay, and we are applying a load P. Suppose this is tensile load, okay. Now we can say that stress equals load by area, stress equals load by area. So we can say stress of concrete is equal to load by area of concrete, okay, and stress of steel equals to load by area of steel, okay. And again you know that stress by strain is equal to stress by strain equals to Young's modulus, okay. Now you can say that you can put this value of sigma c here, that is P by AC epsilon c equals to EC. So we can say that here P by AS epsilon S equals to ES, and this is EC, okay. Now epsilon C equals to P by AC multiplied by EC, and epsilon S equals to P by AS multiplied by ES. Again, if I say that we're assuming the compatibility equation, that means ES equals to EC, you can say that P by AS into ES equals to P by AC into EC. Okay. Now we can neglect the P, so we can say that AS ES is equal to AC EC. So AC equals AS ES by EC. So this is actually nothing but AS into AM. Okay, please keep in mind this relation, that is AC is equal to AS multiplied by modular ratio. And why I have done next, it will be clear in the next slide, that is why I have done this. AC is equal to AS multiplied by AM. Okay. Now what is our theoretical cross section of the beam? This is the theoretical cross section of the beam. And this is a singly reinforced section. Okay, because reinforcement is providing in the tension zone only. Okay, to resist the tensile force. Okay, this is called a singly reinforced section. And you know that the bending stress diagram for a homogeneous beam, this is the bending stress diagram. Okay, and this is obviously a three-dimensional figure. In the last class you have you know that this is a three-dimensional figure. Okay, suppose this is the B. Now you know that bending moment is equal to nothing but C multiplied by lever arm or T multiplied by lever arm. Okay, and C is actually sigma C multiplied by area of concrete into lever arm, that is bending moment, or we can say sigma S into AS that is T, into lever arm. Okay. Now you need to calculate C or T, because you have a three-dimensional bending stress diagram or figure, three-dimensional figure, and you need to calculate, or if you calculate the total volume of this three-dimensional figure, you can calculate C. Okay. So now what is the problem? Suppose this is the compressive stress. Okay. Now what is the problem is, if we have a particular exactly rectangular block, we don't have any problem, because all stress are same here. Okay, all stress are same here. So this value is sigma C. Okay, and if I multiplied with the cross section, and this is the cross section, if I multiply with this cross section, we can get exact C. Okay, exact C. That's I have told you, sigma C multiplied by AC, and it is possible only that case when the bending stress, three-dimensional bending stress figure is the rectangular one. But this is not rectangular one, this is triangular. What I can do? You just understand, try to understand that we need C, we need to calculate C. Okay, that is compressive force. Okay, and to calculate the compressive force, we can multiply the sigma's value with area. Okay, so in this block, this is suppose X, this is suppose Y, and this is Z. Okay, now to calculate, suppose height of this block is Z, length of this block is Y, and width of this block is X. And if I ask for the if I ask the total volume of this block, what I can do? I can multiply it X multiplied by Y multiplied by Z, nothing else, and X is nothing but sigma C, and Y and Z is nothing but AC. Okay, so if I multiply sigma C into AC, we are actually calculating the total volume of this three-dimensional rectangular block, that is X multiplied by Y multiplied by Z. So this is not a problem to calculate the actual C, but the problem is that we have a triangular three-dimensional stress. Okay, so how you can calculate the volume of this block? You can calculate, you can just calculate the area of this block. You can calculate it. How? Suppose this dimension is suppose X, and this is Z, and this is Y. Okay, now what you can do? This is Z and this is X, so you can say that half multiplied by X multiplied by Z is the area. This area is not actually this area. Okay, this is totally different. Okay, you are calculating the volume of this block indirectly. Okay, half into X into Z, that means the area of this triangle, if I multiplied this area with y, we can get the volume. This is y. Okay, so half multiplied by x multiplied by z is the area multiplied by width of the block, that is y. Okay, now this x is actually sigma c, and this z is actually depth of the neutral axis from the topmost fiber. Okay, so this distance, if I say this distance, if I say this total height of this beam is d, total height of this beam is d, then if I consider this neutral axis depth in terms of d, okay, then we can say that this is kd. Okay, so k is a constant, multiplied by d we can get this distance, and we need to calculate the k. I will show you the how we can calculate k. Okay, no issue. Now this z is actually kd. Okay, and this y is actually what? The y is actually b, width of the beam. Okay, this is the b, or this is y. Okay, this kd is actually this kd is actually z. Okay, and this stress value, maximum stress value is sigma c. Okay, so we can say that half multiplied by sigma c multiplied by kd multiplied by b, we can get total compression. Okay, we can get total compression. Now you need to see from another point of view, that is from tension side. Okay, now here is the problem, because the tension, in tension side there is another material, that is steel. The another material is steel. So we cannot directly calculate the value of tensile force, because the material is another material, that is not like concrete. So what we have to do, we can find a relationship between the steel and concrete, that we can replace the steel by some amount of concrete. How we can do that? Suppose this is our theoretical singly reinforced beam. Okay, this is our theoretical singly reinforced beam. Now what is the bending stress diagram? You know that this is the bending stress diagram. Okay, now this is actually not correct. This is actually not correct for this type of beam. Okay, for this type of theoretical beam, this bending stress diagram is not correct. So what is the correct bending stress diagram? The correct bending stress diagram should be this. Above the neutral axis, we have nothing to neglect. Okay, above the neutral axis we have nothing to neglect. That's why that is pure concrete. So we can directly draw the bending stress diagram, that is triangular one above the neutral axis, no problem. Okay, but for the tension zone there is no concrete, so there is no line of bending stress below the neutral axis. There is only the stress value.
স্যার
yes
বলছি 11:06 11:30 থেকে সলিড মেকানিক্স আছে।
হ্যাঁ 11:30 থেকে আমি এখানে শুরু করেছি মোটামুটি ওই 10:30টায়। আমার এখানে লোড সেটিং ছিল, আমি শুরু করতে পারিনি। তো
আমাদেরও তো একটু গ্যাপ দিতে হবে স্যার, মাঝে
স্যার একটুখানি স্যার, হ্যাঁ
ওকে, তো তোমরা মানে আর একটু 10 মিনিট।
ঠিক আছে স্যার, 10 মিনিট ঠিক আছে না? ঠিক আছে
ঠিক আছে, আসলে লোড সেটিং ছিল যার জন্য আমি
হ্যাঁ
start
ঠিক
করতে
আছে
পারিনি।
ঠিক আছে।
So we can draw the maximum bending stress value at this stage, and this is nothing but the layer of tension reinforcement only. Okay, this is the layer of tension reinforcement. So we don't have any triangular shape below the neutral axis, please keep in mind. Okay, now if I draw the three-dimensional figure, you can see that this will be the figure. So below the above the neutral axis, this is the three-dimensional block, and below the neutral axis there is only one layer for particular tension reinforcement. Okay, is only one layer for particular tension reinforcement. Okay, so already you have know how you can calculate C. Okay, so this C is nothing but half multiplied by stress sigma C multiplied by neutral axis depth KD multiplied by width of the beam B. Okay, now how we can calculate T? How we can calculate T? So you know that T is equal to, T is the force is equal to stress multiplied by area. Okay, and for this case we don't need to calculate the diameter of the steel or B or D like that, because we have a ready-made reinforcement manufactured by some industry. That's why we don't need to think about the diameter. Okay, we just consider the area of the reinforcement. Okay, and you know the value of sigma s. So value of sigma s is this permissible stress given by IS 456. Okay, this is given by IS 456 and this value, and there is an area. So we can say moment in terms of tension is equal to sigma s multiplied by AS multiplied by lever arm. Okay, now please keep in mind one thing. This is the last slide, and we denote the stress of concrete by sigma CBC always in working stress method. Okay, sigma CBC, and we denote stress of steel in terms of sigma ST. Okay, always. So this C is nothing but concrete. This C is nothing but concrete. This B is nothing but bending. Before bending, and this C is nothing but compressive zone. Okay, and this S is nothing but steel. And this T is nothing but tension zone. Okay, please keep in mind, we always denote the stress of steel in working stress method by sigma CBC and stress of steel in working stress method by sigma ST. When from the next class I use this term sigma CBC and sigma ST. Okay, so I stop here. From the
Yes,
next day I shall start the working stress method. Okay, the theory and all those
Yes.
equation I shall start. Okay.